Welcome to the 5.6 notes. These notes are about determining concavity of functions over their domain, and then another word which is not up here, which is the inflection point. So first off, if we just look at these graphs, this doesn't have anything to do with calculus, but we talk about concavity. And so here are just like some different examples of concavity, and I'll give you kind of some like key phrases that I use. So if you look at both of the concave up ones, this is an example of a concave up function that's decreasing and a concave function that is increasing. And if you look at both of them, the way that I kind of distinguish between the two of them is this feels more like a cup to me. So one example I've heard before is like if you were to pour water into one of these like piles here, it would stay in, it would like fall, and then it would get caught at the bottom. And so concave up tends to look more like a cup, and then these two examples at the bottom are concave down, and they kind of tend to look to me more like a slide. For example, like if you put water on here, it would just like slide right off. It would slide right off versus these, it would kind of stay in, it would kind of stay in. And so that's like one way to identify just with your eyes whether a function's concave up or concave down. But then there's another trick that also I feel like is pretty helpful. And a function is concave up when the slope of the tangent line is increasing. And so this isn't the trick, but that is like the actual definition. So a function is concave up when the slope of the tangent line is increasing. So let me show you first on the concave up increasing function. So if I draw a bunch of tangent lines, so I don't know exactly what these slopes are, but they're all getting bigger as they go. And so this one right here is like closer to 0. So let's say it's probably closer to like 1/4. This one's looking like more like 1/2, 3/4, 1. I don't know how accurate that is, but as we go from left to right, the tangent line is increasing. And then over here, if I were to draw tangent lines of the concave up but decreasing, they're still actually increasing. And this one's like a little harder to think about, but like this right here is -1. This is -3/4. This is -1/2. And so they're getting less negative, aka they're increasing. And so this comes to my hint that I was talking about a second ago. One way to be able to quickly tell like whether something's concave up or concave down is if when I went to draw the tangent lines, you guys might have noticed, is that I drew the tangent line under the curve. Because if I would have drawn it above the curve, it would have intersected the tangent line. So like, for example, if I would have drawn it right here, it would have like intersected it. But if I do it on the outside of the curve, like under it, it's not going to. That's a bad tangent line, but hopefully you understand what I'm saying. And so another easy way to identify it is that when you draw your tangent line, you draw it under the curve. Under curve. And so concave down, that's not how you spell curve. So concave down is when the slope of the tangent line is decreasing. And again, one really easy way to identify that is when you go to draw the tangent line, you would do it above the curve. So when I go to do the tangent line, let's start with the concave down and increasing. Each time I do this, I'm drawing them at above, and then again, my tangent line's decreasing. So say this is, the slope of this line is about 1, 1/2, 1/4. That number is getting smaller. If I were to do it over here, the slope of the tangent line is again decreasing. These tangent lines are getting worse and worse as I go, but this is like -1/2. This is -3/4. This is -1. And so that's becoming more negative, and so it's decreasing. So those are the two like big words that we're going to talk about today. And then there's one more, which is inflection point. And you have an inflection point when concavity switches. So when it goes from up or down. And we'll look at some examples of that in a second. And then we'll talk about how this connects to calculus in a little bit. But let's start with this. This is just a normal function. There's no calculus. This is just some recap of hopefully things we've heard about. So we're going to talk about where's the function concave up and where is it concave down. And I'm just going to start from left to right. And this just takes a little bit of practice. The inflection point is kind of tricky too. But okay, right here, this whole section, if you guys notice, this is feeling more like a cup to me. If I poured water down there, it would stay and it continues to be like a cup. Anytime, any like place on that section that I highlighted, if I were to draw a tangent line, I would have drawn it under the curve. And so it is concave up so far from -infinity to -1. And again, I'm just writing the x values. Then right here, it tends to switch. It seems like now, okay, this is looking more like kind of a slide to me. If I were to draw the tangent line, I would draw it above. And it continues to be like that. It's kind of hard. I know that it's switching. It's a little hard to see, but I'm just going to say it switches right there. It's a little hard to tell exactly where that happens. But then from right here and on, it goes back to being a cup, and then it continues to be like that. From there on out, if I were to draw the tangent line, I would draw it below the curve. And so it's concave up from negative infinity to negative 1, and then 2 to infinity. And then it's concave down from negative 1 to 2. And so where are the inflection points? Well, their inflection points are where it switches concavity. So there's an inflection point right here. I'm just going to write IP. And then there's an inflection point here at 2 IP, inflection point. So that's where it switches from concave up to concave down. So let's look at another example. Which of the labeled points in the graph are inflection points? So again, I'm just going to highlight. So going down, but it's kind of a cup, and then it stops being a cup at B. So I'm going to say that B is 1. Then this is concave down, continuing to be concave down. This is kind of a weird thing that's happening at E. It's just a point, but it actually is still concave down for that one, because I would still be drawing my tangent line above the curve, and I would still be drawing it above the curve. I'd still be drawing it above the curve. It switches at G. That, at this point, you guys notice it switches concavity here, and it starts to feel more like a cup. And so my points of inflections are at B, right here, and then at G. So where does calculus fit in? Well, one thing is it's kind of hard, like on these two graphs, to know exactly where the inflection points are. And maybe you're like, okay, I kind of see what you mean, but that was confusing. Like, how do you know it happened exactly at that point? And why didn't it happen, like example in this one? Why didn't it happen at 1.5? Why didn't it happen at 2.5? So that's why calculus is going to be helpful for us, because it's going to be able to tell us exactly what is happening. Now, this is going to be a lot, and this is why we have those graphic organizers to, organize all our thoughts. So f of x, this is the new stuff. F of x is concave up when f prime of x is increasing. So f of x is concave up when the derivative is increasing. Now, okay, I clipped here because I was getting confused for a second, but going back over this. F of x is concave up when f prime of x is increasing. So that is a new fact. But let's remember one thing that we've learned earlier this week. The original function is increasing when its derivative, so it's increasing when f prime of x is positive. Bear with me for a second. So f of x is increasing when its derivative is positive. And so, therefore, f of x is going to be concave up when f double prime of x is positive, because if you have an original function, if the original function is increasing, then its derivative is positive. And so f prime of x's derivative is f double prime of x. And so that means that the second derivative will be positive. And so that's the connection. And I'm going to kind of write this out in the little chart to help us out here. So if the original function is concave up, then the derivative function is going to be increasing. And based on what we learned last week, that would mean that the double derivative graph is going to be positive. And so that's how they all connect together. Likewise, f of x is concave down when f prime of x is decreasing. And again, remember that if you have original function and the original function is decreasing, that means that the derivative of it is negative. And so the derivative's derivative is the double derivative. And so that means that if f of x is concave up and f prime of x is decreasing, then that means the double derivative has to be negative. And so your connection there would be the same thing as the little chart above. And it would be concave down. It would be decreasing, and it would be negative. And so those are two new facts. And then an inflection point is what we talked about. It's when concavity switches. And so an inflection point then would increase when the double derivative is 0 or does not exist, and then the concavity changes on either side of the point. And so if you were looking at the double derivative, you would be looking to see where does the double derivative switch from positive to negative. If you were trying to identify a double derivative from the first derivative, if you were trying to identify an inflection point from the first derivative, you'd be looking at where it switches from decreasing to increasing. But the big idea with inflection point is think it's a critical point, essentially, but it's on the second derivative, not the first derivative. So it's like a critical point, but for the second derivative. So the process you use to find an inflection point is pretty much the same as the process of using a critical point, but instead of using the first derivative, you use the second derivative. So let's recap a couple things. First derivative of a function. It tells us about critical points, which is where they're possible extreme, and it tells us, wait, hold on, sorry. First derivative of a function tells us about critical points, which is where there are possible extrema and switches between increasing and decreasing. And the second derivative of a function tells us about inflection points, which is where there may be a concavity switch. And so the first derivative of a function is still communicating to us things about the original function. So it's still telling us where the original function is increasing or decreasing. It's still telling us where the original function has extrema. And the second derivative is still going to communicate stuff to us about the original function. It's going to tell us where there's inflection points and where there's a concavity switch. But it's still communicating things to us about the original graph. So let's just look at 3 examples right here to kind of put all of this together. So real quick, f of x equals x cubed. So its derivative is 3x squared, and the derivative of 3x squared is 6x. So those are the equations of the first, second, and third derivative, the original first and second derivative, and then those are the graphs. And so if I just look here, this says state where the function is concave up or concave down. So I'm just going to use my highlighter. And this is concave down because it's looking like a slide to me. And then it stops being concave down right there. So concave down. So it's concave down from negative infinity, and just assume those are arrows, to 0. And then it'd be concave up for the rest. So concave up. So that is from 0 to infinity. Okay, so then the second derivative, or the first derivative, let's just look where it's increasing or decreasing, because we said that it's concave up wherever the derivative is increasing or decreasing. So if you look here, it's increasing from 0 to infinity. And then it's decreasing from negative infinity to 0. Negative infinity to 0. And then this is the derivative, and this says state where it's positive / negative. So where is it above the x-axis? Where is it below? So it's positive from 0 to infinity, and it's negative from negative infinity to 0. And if you guys look, these all match, right? And these all match. And so that's what you're going to see every single time. So if it's concave up, you're going to see the first derivative increasing on that interval, and you'll see the second derivative being positive, aka above the x-axis. And then you'll see, if you see the original function concave down, you'll see the derivative decreasing, and then you'll see the double derivative being negative. So let's do some problems, but we're going to do some algebraically, and then we might only do algebraic ones on these notes, and then I think we'll do some of the graphical ones in class. But example 4 says f of x equals 3x to the 4th power minus 16x cubed plus 24x squared plus 48. Find the x values of the inflection points, and then state on which intervals is the function concave up and concave down, and justify your answers. So as soon as you see the word inflection point and concave up and concave down, you need the second derivative. If you had the graph of the first derivative, you would be able to figure this out, and we'll talk about that later. But if you're given an algebraic problem, you need the second derivative to be able to solve this. And so your first step is going to be find f double prime of x. And so you'll start by finding f of x, which would be 12x cubed minus 48x squared plus 48x. Then you'll take the double derivative, and you should get 36x squared minus 96x plus 48. And then to find the inflection points, so what we just talked about earlier in the notes is that inflection points happen when concavity switches from up to down, and concavity shows up on the second derivative. Concave up shows up as being positive. Concave down shows up as being negative. And so for those to switch, you would have to go through the x-axis. And so just like we were doing with critical points, you're going to set equal to 0. So you're going to set the f double prime equal to 0. So I'm going to do 0 equals 36x squared minus 96x plus 48, and then I will factor. So, and if you don't feel like factoring, you can use the quadratic formula, just don't use it wrong. But I'm going to pull 12 out of all of these, so I'll get 3x squared minus, 8x plus 4. And then I have to factor by grouping, so I'll do 3 times 4, which is 12. And then -6 and -2 multiply, so 12 and adds up to -6. So then and remember, you only factor by grouping when the a value is not equal to 1. 3x I'll pull out, x minus 2. I'll get 0 equals 12 times 3x minus 2 times x minus 2. And then I'll set 3x minus 2 equal to 0. And you'll get x equals 2/3 and x equals 2. So these are possible places there could be inflection points, but a condition of an inflection point is it has to switch concavity. And so we're going to have to figure out all of these things, to figure out the inflection point, and then also to figure out concave up or concave down, we need to do a line test. Line test. And this will be so similar to what you've been doing for increasing or decreasing, and really similar to what you've been doing for relative min and relative max. And so I'll start here, and I'll just plug numbers in to the second derivative because I'm concerned about where's the second derivative, positive or negative. So I'm going to start with, I'll plug in 0 first. If I plug in 0, and I like to plug it into the factored form, so I would get positive times a positive times a negative, so that would give me a negative. I'll plug in 1 next. This would give me a positive times a positive times an, oh, sorry, this first one should have given me, sorry. This is a positive times a negative if I plug in 0. So this will be positive. If I plug in 1, I get a positive times a negative. So this would be negative. And then if I plugged in like 3, I'd get a positive times a positive times a positive. So I have my line test. I plug things in, and then I just have to answer my question, and then I have to justify my answer. So let's start with inflection point. So there's an inflection point. And you'll write inflection point at 2/3 at x equals 2/3 and x equals 2, because the double derivative switches, you could put just switches signs there. Switches signs there. So that's what you could say about inflection point. Big idea is it switches from positive to negative or negative to positive, and then that means that there's a concavity switch because that's the connection. And then you also have to answer the part about concave up and down. So you would say concave up between negative infinity to 2/3 and 2 to infinity, because the double derivative is greater than 0. And then the final thing would be concave down between 2/3 and 2, because double derivative, I keep doing a double F, sorry. Double derivative is less than 0. Okay, we'll do, and so that's the answer. And so that's all you got to do. So it really should feel similar to the process that you were doing before, but just with the second derivative instead of the first derivative. So we're going to do 2 more examples real quick. Okay, so where does the graph of y equals x minus 2 to the 1/3 power have a point of inflection? So we need the second derivative. Start with the first derivative. This is the chain rule, but it's a pretty easy chain rule. It's inside function, outside function. So the outside is 1/3 x minus 2 to the negative 2/3 power. Remember, this is just the power rule. But then the reason it's an easy chain rule is because the derivative of the inside is 1. So I don't even really need to multiply that. Now I'm going to find the double derivative. So it'd be 1/3 times negative 2/3 times x minus 2 to the negative 5/3 power. Again, derivative of the inside is 1, so it doesn't matter. And now I'm just going to simplify this real quick. So I'm got to stop doing the double F's. Okay, write that like that. So I'll have negative 2 over 9, and then I'm going to move this to the denominator to make a positive like this. So that's our double derivative. So I'm going to start by setting it equal to 0. We haven't actually had one of these problems in a while, but one of the conditions earlier for a possible inflection point is one that the double derivative has to equal 0, and then the concavity has to switch, or that the double derivative couldn't exist. And in this case, if I plug in 2 right here, I'm going to get a 0, and I'm going to be dividing by 0. And in all the other cases that's happened, that x value didn't exist in the original function, but you could plug in 2 into this original function. Your answer would just come out to be 0. And so this one actually does have a possible inflection point at 2. So there's one possibly at 2 because it doesn't exist there. D and E there. And then, okay, envision solving this problem. If you were to solve this problem, one of the things that we've been doing when x is on the bottom is we've been multiplying both sides by the denominator. And if we ended up doing that in this case, it would actually just go away, because if I did it on the left side, right, these would cancel out. And then if I did it on the other side, it'd be multiplied by 0, so it'd cancel out. So we're actually not going to be able to, like, there's no value of x that would make this double derivative equal 0. And so the only place there's a possible point of inflection is at 2. So I'll plug in 2 here, and then I'll do my line test. And so if I plug in a positive 1, you would be doing 1 minus 2, which would be a negative, and you'd have a negative over a negative, so this would be positive. And then let's say I plugged in 0, I would have a negative over a negative. So that would also be, oh, sorry, I did this wrong. Okay. So let's say I plugged in 3 first. If I plugged in 3, I'd have a negative over a positive. So that should be a positive. And then this should be a negative. Like if I plugged in 1, I would have a negative over a negative. Sorry, I think I just said that wrong. And so there's a point of inflection. That's all it's asking. It's not asking for concavity, but point of inflection at x equals 2 because f double prime of 2 does not exist, and f double prime of x switches from negative to positive. From negative to positive. Okay, we're going to move on to one more example, and then we'll finish these notes in class. Okay, example 6, find the x values. Oh, actually, one other thing that we need to do for this one. So if you look at the difference between these instructions and the other ones, is that this one says find the x values of the inflection point. This one says find the x values of the inflection point. This one just says find the inflection point. So the one other thing we do have to do for this is we need to find the y value of this inflection point. So to find the y value of the inflection point, the double derivative just tells us that the inflection point happens at x equals 2. But if we want to find the y value, we plug it back into the original. So I'm going to do 2 minus 2 to the 1/3 power. That equals 0 to the 1/3 power, which equals 0. So the inflection point specifically happens at 2, 0. So just to add that. Okay, but going on to this last problem, we'll do it real quick. We start by finding, let's read it, I guess. So g of x equals 1/4 x to the 4th power minus 4x cubed plus 24x squared. Find the x values of the inflection point and then state on which intervals is the function concave up and concave down. So inflection point's concavity, I need the second derivative. So this will be x cubed minus 12x squared plus 48x. So that's the original, or sorry, that's the derivative. The second derivative will be 3x squared minus 24x plus 48. I'm going to set this equal to 0. To factor, they have a greatest common factor of 3, which helps us out a lot. So this will be x squared minus 8x plus 16. And then this is actually a difference of squares, or it's a perfect square binomial. So I'll just write it out for you guys. Well, the two things that multiply to 16 and add to negative 8 are negative 4. And so we only have one solution here, and that's x equals 4. So let's go to test this out. I'm going to plug in 4. So if I plug in like a positive 5 here, so if I plug in 5 here, I'll have a 1 and a 1 times a 3. And so that will give me a positive number. Then if I plug in, like, let's say 3 here, I would have a positive times a negative, which will make a positive. And this doesn't normally happen, but on the left side it's positive and on the right side it's positive. And so it's going to be, there's no inflection points because it never switches, but it's going to be concave up from negative infinity to infinity because f double prime of x, I did it again, sorry. F double prime of x is always positive. So that's your answer, and that's where you guys can stop. If you want to look at some of the next ones, you're welcome to, but I'm going to stop there.